Good afternoon, class. This is week 2 Wednesday lecture. We're going to finish up the chapter on Cartesian vectors. Part of it might be a review from maybe last time, a few of the elements we'll talk about. I'll also tell you at the beginning, I've got 2 example problems I'm going to do. And the example problems are listed in Canvas. The chapter 2 example problems. And if there's a way you can get hold of, I'll show you the problems on the screen, but I'm going to have to go back and forth when I work it. It'd be nice if you could look at the problem while we're working it here. So that's up to you. The problems are in your textbook and on Canvas. So you can take a look at the ones on Canvas if you want to stop the video and copy them or find them in your textbook. Okay, so we'll start. Share the screen. Cartesian vectors. Well, what we have is three-dimensional space. We have a x-axis, y-axis, and a z-axis. It's three-dimensional space. I'm going to define, starting at the origin, we'll have a vector A. And again, I designate a vector, put a bar across the top that indicates a vector quantity. And we have the direction cosines. These are the angles that describe this vector with the x, y, and z axis. The angle with the x-axis is the alpha. Angle with the y-axis is beta. And the angle with the z-axis is gamma. And those are, we'll call those direction cosines. So the vector A, we can write with unit vectors. We've talked a little bit about the unit vectors. The x-axis unit vector is I, the y is j unit vector, and the k, or the z is k unit vector. So I can write this unit vector A as the magnitude A sub x I plus the magnitude of A sub y j and the magnitude of A sub z k. Okay, so, and the scalar A is simply the square root of the A sub x squared plus A sub y squared plus the A sub z squared. Pretty easy calculation to get the magnitude. The direction cosines, cosine of alpha is the scalar A sub x divided by A. Cosine B is A sub y divided by A. And the cosine gamma is equal to A sub z divided by A. So those give you the direction cosines. They locate that vector A in three-dimensional space. So with the vector direction of A, the unit vector, we can describe a unit vector along A also. Okay, this is a vector quantity. We talked a little bit about unit vectors. So we can define a unit vector along A. And the unit vector is the A sub x divided by A sub y divided by A j plus A sub z divided by A k. And the resultant is the sum of the forces in the xi plus some of the forces in the yj plus some of the forces in the zk. And so we can write the vector A as the magnitude of A, scalar quantity of A, times the unit vector of A. And this is, we've talked about this alternate way of writing a vector quantity if you can define a unit vector for that quantity. Position vector. Position vector is a fixed vector in space which locates a point in space relative to another point. So we have our XYZ axis. Pick a point out here in space. Call that point P. And the position vector, we're going to reference it from the axis system, is just going to be the XYZ coordinates, or the IJK coordinates of that point P, because the other end of this is 0, 0, 0. So the position vector for a vector reference from the axis, origin of the axis, 0, 0, 0, is just the x, y, z coordinates. So it's xi plus yj plus zk. Real simple. Now, if you want to describe the position vector between 2 points in space, so we have A and B, what we'll do is for the I component, we just subtract the xb, we'll subtract xa from that. So we have xb minus xa, that's I direction. And then we subtract the yb from the minus ya, and that's in the j direction. And for the z, it's zb minus zak. And so we have the position vectors designated in the ij and k direction. A little bit more to it when you have 2 points that are in space and not one at the origin. So that's the definition of position vector. Dot product. And there's I consider it an engineering application we can see directly with one of the example problems why this can be significant. Dot product, say we have 2 vectors, A and B, angle between the two is theta, and we're going to limit theta between 0 and 180 degrees. All this applies between 0 and 180 degrees. Dot product, A dot B, scalar, is just the scalar AB times the cosine of theta. Okay, so this is a scalar product. A dot B is the same as B dot A, same value. You can multiply A dot B by some factor. Okay. And you can do it, you can take this factor and multiply it times A and then do dot B, or you can do A dot B with that factor associated with B. It doesn't matter which way you do this, but you're only going to multiply by whatever the factor is by one of the designated points, either A or B in this case. Okay, here's the important part of this. There are two applications for the dot product. A dot product can give you a projection perpendicular to some line in space. And the one that we're going to look at today as an example, and one that might have practical applications, I think particularly to the mechanical engineers, is a projection of a force along some line. And that force, that basically that projection is going to be a dot product of that force dot product with that unit vector along that line. So F, the vector F dot unit vector, and that unit vector is going to be along the line, will give you the maximum, give you that force projection along that line, which is going to be this, what we call this FB right here, the force projection. So force vector directed along a line. We'll talk about this as a unit vector. So we have a line AB. We can define a position vector R between A and B. Okay, so this is the force vector, and we're just selecting a couple of points along here. So there's a position vector that takes the same line as this force vector here. So we're describing that position vector along that force line vector. So as a Cartesian vector, this is going to have the same direction as a position vector, which means that this unit vector along force vector can be written as a position vector divided by the magnitude of the position vector. This is a very easy way to determine unit vectors, and we'll do this in a problem in a few minutes as we go through this. So the force F as a Cartesian vector has the same direction as position vector. And with that being the case, we can define the unit vector then basically is the same, has the same direction as the position vector. So the unit vector is equal to the position vector divided by the magnitude of the position vector. And so we can write the vector F as the scalar of F times the unit vector. And this is actually it's a simple equation, but it's a very powerful equation in defining vector quantities and working problems with vector quantities. Because given the type of problems we're going to look at, we're going to be able to define these position vectors relatively easy, even in three-dimensional space. And I'll show you that. Okay. This is example problem 293. And let me show that to you. If I can get this. To work. This is the problem in your textbook. It's 293. see if I can get this set up decently. We have two forces. This is a flagpole. I'm trying to get this thing oriented so you can see it properly. This way. Got two forces oriented, and there's force B is equal to 560 newtons, and this is a force if I can focus this. Get all the tools up on this. This visualizer is relatively new. I have not used this very much, and I'm still trying to work on it. There is a focus. Yeah, I'll do the best I can with this. So we have a flagpole. We've got two forces. This is F sub B, and F sub C starts at A and ends over here at C. This is point C, so there's a cable here. And what we want to do is, with these the two forces are given, the magnitude, we want to add those two forces together to give us the resultant force acting on this flagpole. It's going to be out here in some direction acting on that flagpole. We're given dimensions. I did pause here just a second. There's another example problem that is in that that you'll find in Canvas when I looked at the example problems in this chapter. I chose not to do that problem. It uses angles. I don't think I would ever give you a problem using angles rather than dimensions. This is much easier to work with, and I think it makes a little bit more sense to use dimensions. And most problems are shown this way. They're not shown with angles. Take a look at that other problem that I have listed in there. Okay. So the way we do this, we're given the magnitude of FB and the magnitude of FC. To add these together, all we need to do is get the components, the X, Y, and Z components, and add these together. And we can find a magnitude and direction cosines and all that. In order to do that, we need to define the unit vectors. Okay, we know what the magnitude of the force is. If we have the unit vectors, we can write this force as a vector quantity, and we would have the IJK components, or the X, Y, Z components. So that's what we're going to do, is find the unit vectors. And I'll just show you what we're doing here very, very quickly when we do this. I'm gonna look A to B. I want the unit vectors on that. So what we have to do is look at the way that this is dimensioned. Okay. So the I component, here's the x-axis, here's the y-axis, and this is the z-axis out this way. So if I'm going A out to here, what is the x component going to be? The dimensions. looks like it's this dimension out here. You have to orient yourself to the way the 3 dimensions is going to be shown on the diagram. The rule is if you have dimension lines, they'll be parallel to the axis. So these dimension lines parallel to the x-axis. These dimension lines are parallel to the y-axis, and these dimensions, or this one dimension here, is parallel to the z-axis. So if you just keep that in mind, you should get these actually relatively easy. Okay, as you go through this. So that's the problem we're going to take a look at. So for the a-axis off there, I said the I direction was 2. We could find the j dimension is -3, and the k dimension is -6. The unit vector then is that position vector divided by the magnitude of the position vector. The magnitude of the position vector is the square root of 2 squared minus 3 squared minus 6 squared. It's that simple. And this denominator comes out to be 7th. So this is the unit vector for A. 2/7 I minus 3/7 J minus 6/7 K. Okay, so for the other force C, it's basically the same thing for the unit vectors. Again, I just want to get the dimensions. The dimension for the unit vector for C is 3I plus 2J minus 6K. The magnitude of R then is the square root of 3 squared plus 2 squared minus 6 squared. Again, this denominator comes out to be 7. And so it's 3/7 I, 2/7 J, minus 6/7 K. So the force vectors, FB and FC, we can write the force vector as the magnitude of the vector times the unit vector. Well, the magnitude is given to us in the problem. So the magnitude of the force vector B is 560 newtons. We multiply that times the unit vector. This is the unit vector up here. Okay, 2/7 I minus 3/7 J minus 6/7 K. And so we get F sub B take 500 and multiply it times each of these, the I, J, and K. And so we end up with F sub B is 160I minus 240J minus 400K newtons. We do the same thing for F sub C. It's the magnitude of F sub C is 700 times the unit vector for C. This is unit vector for C. So it's 3/7 I plus 2/7 J minus 6/7 K, which is right here. And we can get the force in C then as a vector quantity. We just multiply 700 times each of these terms, the IJK terms, and we end up with 300I plus 200J minus 600K newtons. Resultant force, we add these two forces. Okay, the resultant is F sub B plus F sub C, written as vectors. Okay, with IJK. So we get the IJK components, that addition, and that's going to be the resultant. So we add the two I's, the two J's together, and the two K's, and we end up with this quantity down here. 460I is 400J minus 1080K. And the magnitude, we know how to get the magnitude. It's just the square root of the sum of the squares of each of the components. So it's 466 squared minus 40 squared minus 1080 squared. And when you calculate this, you get 1174.56 newtons. You know, that's your calculator running this out. But we said, as a rule, if you gave me this answer, if this was a homework problem to work or an extra credit problem or a test question, I'd say, okay, yes, mathematically this is the correct answer. But if you say this is the answer to this problem, I'm going to ask, well, so you measured out to what? Hundredths of a Newton? Well, you didn't. Okay, maybe 1 Newton, but sure not hundredths of a Newton. So we need to round this to 3 significant figures. And so the 3 significant figures we can't is 117. And so what we need to do is be able to write that 117. And we want to do the fundamental units, and fundamental unit is kilo, okay, that we have. And so if we move this 3 places, it gives us 1.17 kilonewtons. Okay, that's a fairly standard unit of measurement in the SI system. We sort of did some example problems in chapter 1. So the answer would be 1.17 kilonewtons to 3 places. The direction cosines, we have equations for those. Just plug in your magnitude of the force in the x direction, which is 960, inverse tangent 960 over the magnitude, and you can use 1174 for that. That's fine, 1174. You get an angle 66.9. You get a direction cosine over here and a direction cosine over here. This one is going to be 180 minus, and it's 180 minus, okay, with those angles. So these are the direction cosines. For that resultant force. So that's a 3-dimensional problem. Second problem I want to do is a projection problem. problem 125 in your textbook. We have a piece of equipment, and we have an 800 Newton force applied to this arm out here. Okay, it's a tension force, and what we want to know is the projection of this force down here on the U-axis. That's the force that's going to be attached to this. And your book this didn't copy real good. This is the nice, use color pictures, really good drawings in your textbook. There's a centerpiece in here. It's circular piece of steel. As an engineer, if you're looking at some type of a mechanical component here, and you want to design this piece down here, a circular piece, what you need to know is the total force acting along that force, this center line into this circular piece of steel in here. And you want to design for that. The only way to design for that is to know that total force. Once you know that force, you select the material, and you'll know, this is strength materials, you'll know the stress, and you're easily going to select a area that would accommodate that force. But the first thing you need to know what that force is. And so this problem, this dot product, can give us this projection of this force, 600 Newton force, along this U-axis. Okay, so that's the problem that we're looking at. And so, again, we have a force. What we want to do is get the unit vector. I'm going to sort of sketch this out just a little bit. I guess we can take a look at it this way. So we need to know the magnitude of the projection of F along U. Okay, this is U. And so we need the unit vectors. Unit vector along this force, this axis system here, U. And so the unit vectors, and again, if you look at the diagram down here, you can get the dimensions. The dimension is 2i, 4j, and 4k. Okay, so that's the unit vector. And again, we've got all the dimensions given up here, so we can, I don't know if you can pick them off this this diagram real easy. But you got the dimensions to be able to get this unit vector. These are the dimensions. And so the unit vector O to A are the dimensions, the ijk dimensions divided by the magnitude, again, a square root, some of the squares of the components. And so the unit vector O to A is 1/3 I plus 2/3 J plus 2/3 K. So the force vector is the magnitude of the force vector times the unit vector okay, which we have up here. And the magnitude force is 600 newtons. So 600 newtons times the unit vector gives this force, 600 Newton force. We can just write it as a vector quantity then, 600 times the unit vector. So this is F as a vector quantity. So the magnitude of the projected component is the dot product. So this magnitude is F dot the unit vector of U, so U sub U. So we already determined F, which is this quantity here. And now we want to look at the unit vector for U. All we have for U is an angle with the y-axis, and that's 30 degrees. So if we're looking at the x direction, this is the x direction, and we have an angle, and this is opposite this angle. So we're going to use the sine of 30, it's opposite, as a direction. And talk about this related to the other problem too. The other component is along the y-axis, so used in the xy plane. And this is adjacent. Okay, it's adjacent, so it's cosine. So it's sine 30i plus cosine 30j. Okay, that's the unit vector for U. It's sine 30 for in the x direction, sine 30 in the x direction. In the y direction, it's cosine 30. And so what we have then is this dot product. And the way the dot product is going to work, it's I times I, j times j, k, and there is no k on the unit vector. So it's just going to be the 200i times sine of 30, that's minus 200, plus 400 times the cosine of 30, 400 times the cosine of 30. And then this is 400 times 0. There's nothing out here in the k component. And so we end up with a force along the u-axis equal to 246 newtons. Which means that 600 on this lever in this direction, and we found the direction with the unit vectors, results in a force along this u-axis passing through this assembly down here equal to 246 newtons. What you can do with this now, since you know the force, there's a little centerpiece of steel in here. It's attached to this outer ring. You're going to design for this centerpiece. You now know the force acting along the axis, 246 newtons, and now you can design it. And actually, it's a pretty simple design. And what you do is once you pick the material, there's a strength of materials, that's the class. There's a strength associated with that material. That strength translates to internal stress. Stress is force divided by area. And once you have that force and you know the stress, the unknown is the area. And as an engineer, you can size it. You can say what the diameter needs to be to get adequate area in this thing. And so in terms of dot products, there was a perpendicular to a line. I think this one has the most valuable use from an engineering perspective. So this is the problem I chose to use in here. So this is a dot product application. Okay, that closes our discussion of vectors. Chapter 3 is the first chapter that really looks at what I call the statics problems. There'll be a series of chapters we'll look at that are going to be typical statics problem. And this is going to be the first and the easiest problem we look at, and it's particle equilibrium. Basically, you're adding and subtracting. Okay, that's what you're doing. And we'll start on that next week. And have a good, actually no class on Monday. So Wednesday, have a nice long weekend, stay safe, and we'll be back with you next week.